All right, so let's do 3.1. So the reason we're doing Module 2 and Module 3 together is because they are basically the same concept. So we're still dealing with linear functions. It's not changing, we're just adding a little bit to it. So the key terms, there are a lot, so you might want to make some note cards to memorize these just like you do for social studies. So a relation is just any set of ordered numbers. Okay, so it's a relation if you have ordered pairs. If you can take x and y and put them on a graph, it's a relation. Now, a function is a specific kind of relation. It's where every input, x, is assigned to exactly one output, y. Okay, so input is what we plug into the equation, that's our x. And then output is what we get out of doing the problem, and that's our y. Okay? So it means there's only one x with every single y. So the domain is those inputs are our x values. Okay, so it's a set of inputs, all of our x values, and a range is our set of outputs, all of our y values. Okay, now for those, for our domain and range, we have a continuous. So that's when the domain includes all real numbers, and the graph is going to be a line or a curve. So that's when we connect our dots, and because that's telling us that everything in between is an answer. So remember we talked about that where it could be a half, it could be 1 1/2, it could be -2 1/3. So that's why we connect them, so that it shows that everything in between, and that's also why we put arrows, because it's continuous, it goes on forever and ever and ever, but everything works as well. Now, discrete is when a domain consists of just whole numbers or just integers or both, and this graph is going to be a series of points. So the reason we have discrete answers or discrete functions is because sometimes halvesies and quarters and things like that don't work, and only whole numbers work. Okay, so that's kind of like when we have story problems and we're talking about shoes or people, right? I'm not going to have a half a person, that'd be weird. I'm also not going to just buy one shoe, I'm going to buy both pairs, they come together. A pair of pants, I'm not going to cut off one of the legs. Okay. And then a one-to-one is a specific, it's where no two elements from my domain map to the same element in my range. And we'll go over that, but it just means that everything is perfectly one-to-one, where my x's, none of my x's share my y's. And we'll look at what that looks like. But it's where my x's do not share any of my y's. So we were given this table, and we want to know if this is a function. So remember, a function is just a very specific relation. So this is automatically a relation because it's a set of numbers, right? A set of ordered pairs. I have 1, 11, 2, 12, 3, 4, 13, 4, 13, and 5, 13. So remember, the x's are inputs, and this is my output. And so there's a couple of different ways you can determine if something is a function or if it's just a relation. Remember, a function is specific where my x's only have one y. So really, the first thing we can do is just look at my x's. Do my x's repeat at all? Okay. If they don't repeat, then it's going to be a function. So this is a yes, because my x's don't repeat. Now there's another way you can see that, and it's called mapping. And so what we do is we draw these ovals, and then I list my inputs, and I go 1, 2, 3, 4, 5, and then I draw another one, and this one's going to have my outputs. I'm going to go 11, 12, and 13. And I only put the 13 once because I only need it once, right? Yeah, it comes up a couple of times, but that's okay. So then what I'm going to do is connect them to their inputs, to their outputs. So 1 went to 11, 2 went to 12, 3 went to 13, 4 also went to 13, and 5 also went to 13. And then what we're going to look at is right here. Do any of these have double lines? One line, one line, one line, one line, one line. If they all have one line, then it is a function. Okay, so my x's don't repeat. They have exactly one output to each input. Now, I don't care if my y's repeat right now for a function. Okay, they can repeat all they want. Okay, so yes, this is a function because the x's have one output. Right, the input has one output. Or you can just say the x's don't repeat. Okay, so then they ask us to list the domain and the range. So remember, the domain is my x's. So what we do is just write the list. We have to draw these braces, and I know those are hard for people to draw. And then we would go 1, 2, 3, 4, 5, and then we would close them with the braces. Then the range is my y's, and it's actually going to be very similar to this bubble over here that I drew. So again, braces, and then I'm going to go 11, 12, and 13, and that's it. We do not list the 13 multiple times. It's only there once. The range of the y's is 11, 12, and 13. So it says a function can model each situation. What is a reasonable domain and range for each function? So it's already telling us that this is a function, which means only one y is going to go to every x. And so it's openly telling us that it's a function, so that's good. So what they want to know is what's a reasonable domain? So remember, domain is the x's, and range is the y's. So a hose is filling up a 10,000 gallon swimming pool at a rate of 10 gallons per minute. Okay, so the first thing would be determining what is your x and your y. So the x's are going to be our time. Okay, right? Because time goes on forever and ever and ever. It's independent of everything else. So our time, or our minutes, is going to be x. And the number of gallons is going to be our y. Our gallons is going to be our y. So our domain would be 0 minutes, right? Because we got to start filling it. That's when we start. To how long it takes to fill it. We don't have to be specific. It says reasonable, so that's a reasonable statement. We have to start at 0 minutes, but the ending number is just going to be however long it takes to fill up the pool. Now the range, oh, I almost put y. I want to put range, is going to be 0 gallons because I haven't started filling up my pool, so it's empty. 2, and actually this time we're going to say 10,000 because we know when it needs to stop. If we know that the range has to stop at 10 gallons or I'm going to overfill this pool, it's not going to work. Okay, so your range does have a definite beginning and end because we know where it needs to start, we know where it needs to stop. So that's why these are a little different. All right, so number 2 says a restaurant needs to order chairs for its tables. 1 table can accommodate 4 chairs. So what I want you to do is think about what a reasonable domain and range would be. I don't want you to write it down yet, but just think, like, what would a reasonable domain and range be? I will tell you that the domain is going to be your tables, and your range is going to be your chairs. Okay, so that's kind of a little hint. So what do you think a reasonable domain would be? So the domain is going to be 0 tables, right, before they start filling the restaurant, to the number of tables needed. I'm going to put the number symbol, number of tables needed. oh, not meted. Let me rewrite that so it's in better handwriting. All right, I don't know how many tables the restaurant needs, or has, so it's just 0 tables to however many tables they need. And then the y, or the range, is going to be 0 to 4 times the number of tables. So it's 0 chairs to 4 times the number of tables, because every time I add a table, I add 4 chairs. So it's not just 0 to 1 to 2 to 3 to 4. If I add a table, I automatically add 4 chairs. I add 2 tables, I add 8 chairs, and so on. So this one's again a little more specific. It's not exact like the first one, right? 0 to 10, but it is 0 to very specifically we have to have 4 times the number of tables. Because again, every time I add a table, I add 4 chairs, not 1 chair. All right, so here's our question about discrete or continuous. So what I'd like you to do is try to go read your definitions again of discrete and continuous. And I want you to decide if these are discrete or continuous. So we should have said that this first graph is continuous, because it is connected. All of these are connected, right? So this point exists, this point exists, this point exists. All of these little tiny decimals and fractions that we don't like to graph all exist. Even this y-intercept that is somewhere below -1. So because it's connected, it means everything in between counts. Every little fraction, decimal, repeating, whatever. And this one is discrete because this point works and this point works, but nothing in between works. These are whole numbers and integers. And so this is like our story problems where we're talking about things that can't be cut into pieces or it wouldn't make sense. So whole numbers only or integers only, and that's why this is discrete. All right, so why don't you try writing the domain and range of each of these functions. It does tell you their functions. Think about why they're a function. And then once you do, unpause and see if you got the same thing. All right, so our domain would have been 3, 5, 7, 8, 11. And your range should have been 6, 7, 9, 14. You should have not written the 7 twice. And then for this one, we have -3, -1, 2, 5, 7. And my range. And we need to put them in order, so that's new that I didn't bring up the first time, but when we write our sets of ordered pairs, or sets of range and domain, we actually, no matter what they give them to us in, we need to then put them in order from least to greatest. So I'm actually going to write -7, -5, 4, 5, and then 9. And that's because we always put them in order from least to greatest, no matter which order they give us our domain and range. All right. All right, so this is us practicing, again, if relations are functions, and then we are going to actually add in, are they one-to-one or many-to-one? So we didn't talk about what many-to-one was, but it basically just means that they're not one-to-one. Okay, so there's a couple of ways you can do this first one. Just to determine it's a function, we can just look at our x's. But to determine if it's a one-to-one, we really do need this bubbling that I showed you. And they did like boxes. I've always done it with just ovals, so it's up to you. If you want to kind of do these boxes, you can, or you can do it this way. So we're going to go -4, -3, 1, 3, and then 5. That's my inputs. And then I have another one over here. I'm just going to make it further away just to kind of make my arrows maybe look better. And then for here, I'm going to also put them in order like I did my range. So I'm going to go -11, -8, 4, 5, and then 7. And so the way we determine a function, we first connect them. All right, that one. I know you're like, why did we write them backwards if we're just going to draw all of our arrows upside down? I didn't do a very good job drawing that arrow, but so the first thing we do is check here. Do any of them have double lines? Nope. So this is a function. And then to determine if it's a one-to-one, we then look here. Do any of my outputs have a double line? No. So this is then a one-to-one. Meaning every single one, all of these only have one line as well. Okay, so functions, my x's, and my one-to-ones are my y's. Why don't you try number 4 and see how it goes? All right, so we would go -4, -2, 0, 2, 4. Sometimes it's better to write your numbers than circle them, or draw a little weird box. And then here we would have 1, 4, and then just 8. And again, I can draw my circle or my box. And so we should have connected them. -4 goes down here to 8, and -2 goes to 4, 0 went to 1, 2 also went to 4, and then 4 also went to 8. So the first thing we look at is the x's. All right, they all have one line, so it is in fact a function. And the next thing for the one-to-one or many-to-one, we look at the y's. And if you notice, these two have double lines. So this is a many-to-one, meaning my x's went matched up my y's. Doesn't make it not a function, it just means it's not a one-to-one. 2 of my x's ended up at 1 of my y's, so that's why it's many-to-one. See, many-to-one. All right, try number 5. So number 5 was already like gridded for you. You actually should have said not a function. Because it's not a function, I don't care about the one-to-one and whatnot. It's because right here, if you notice, there's a double arrow right here on -2. That means that that x has more than one y, and it's not a function. Now, when it comes to a graph, the easiest way to determine if it is a function or not is what we use is what we call a vertical line. So I'm going to actually draw a vertical line to the best of my ability, and then I'm going to move it. So it's called the vertical line test, and what you do, oh, it's not moving oh, didn't work, got stuck, is you basically drag your vertical line across your graph, and you want to determine if your vertical line ever hits 2 parts, like it's dragging everything now, on here. Okay, so I'm really trying to show you guys that if you take a vertical line and drag it across here, will it ever hit 2 parts of my graph at one time? And that's what we're looking for. So try, maybe just drag your pencil across it and just drag it across vertically across this. And if your pencil ever hits 2 of them at the one point, then we would say this is not a function. Now, I will tell you that this actually is a function. And that's because the vertical line test would pass. Because, and I know it seems really steep, it's really, really steep, but if you really look, it is moving across the x. See how it just keeps going across the x? None of the x's repeat. There's not another point like right here. This would cause it to not be a function because I have one here and I have one here. So these would cause it to not be a function. But because I don't have that, then I don't have any issues. Now, we would, however, call this a many-to-one. Okay? This is a many-to-one. And I'll show you why. Let me write this. I'm going to go like this. Many-to-one. And here's why. If I look at my y's, remember, for many-to-one and one-to-one, we look at our y's. I have y is 4 here, but I also have y's for here. So it's still a function because this one's at, you know, a quarter, and this one's at negative 2 1/4, but they both hit 4. So the x's are different, but the y's are not. So that's why this is a many to one. If I used this, I would have 4 listed twice, and I would have 2 lines on it like I do here. Okay, so function, we look at our x's. Many to one or 1 to 1, we look at our y's. And since I have 2 here, and I have 2 here, and I have 2 here, it's basically like a horizontal line test. So question number 7, I want you guys to answer, and I want to see if you can answer it. It says, explain how the vertical line test is going to prove that a relation is not a function. So the example we just did, I proved that it was a function because my vertical line only touched my graph in one place. So you explain, how is a vertical line going to prove that it is not a function? So I want you to try that. I'm going to talk about it in class when we get back, so just be prepared to answer that question. All right, Fiona buys different amount of gas at $2.25. She has a graph which shows the difference amount she paid. What constraints are there on the domain of the function? So constraints meaning, does it stop somewhere? Does it start specifically somewhere? Right? Can it be whole numbers? Can it be fractions? So are there any constraints, and what constraints are there on the domain, the x's of buying gas? So again, how about you do this one? Let's have this as a discussion in class tomorrow as well. Okay, so are there any constraints, and what are they of Fiona buying gas? It's kind of like when we did the domain range questions, right? I had to start at 0. I only could go to here, okay? So, similar to those domain and range questions at the beginning. All right, so 2 main things to remember is that a discrete function is going to have only whole numbers and integers, and a continuous function can include all real numbers, meaning decimals, fractions, negatives, and positives. All right, so here's your 2 independent questions. I know I just made you do 2 others by yourself, but here's 2 more. So this is just like what we just did on our graphs and things. Is this a function? And are they 1 to 1 or not 1 to 1 or many to 1? Either or is fine. All right, until next time.